whereby you have the same laser bouncing back off the particles, but the returning signal is Dopplerized. So we can detect a frequency shift and therefore the movement of the particles. And if we scan the laser in different directions systematically, then we can come up with a wind vector as a function of height and give us some nice wind speed profiles. So here we have, with height, we have the wind speed showing us from the end of the day at 5 o'clock in the evening, the profile transitioning to a nocturnal jet. So that's the kind of detail that we can now get continuously using Doppler lidars. Now they could be used in different ways. So dual Doppler lidar is when you have two lidars which are intersecting their beams at a certain point, and they can raise up into the atmosphere, creating something like a virtual tower. This is an exciting new development, and it's particularly useful when you have complex flows in the terrain. So there's some good work coming out of Stuttgart looking at the valley flows affecting that town. You can also get turbulence from lidars. So here we have a profile underneath a cloud. So there's turbulence generated by the city and also by the cloud itself. Again, exciting new data for dispersion modeling. Other measurements are available. I haven't got time to talk about them today. But radar wind profilers, SODAs and RAS have all produced really interesting results for urban areas. Thinking of the thermal structure, it's really important to get the temperature and the moisture profiles in the urban area. So the traditional way of doing this is a radiosonde. Here we have in the Hong Kong Observatory, there's been a very extensive record of releasing radiosondes within the city. They go with the flow, so that you can't control where the measurement is made spatially. And this is very similar to AMDAR. So aircraft such as around New York City can take off. They have measurement packages on board, and we can see a little bit in the urban boundary there due to them. Now, these are kind of rather temporally sporadic measurements. A more continuous measurement is microwave radiometer, which is a passive instrument. It's just measuring the microwave radiation coming in, and it scans at different heights in the atmosphere, does some kind of retrieval process to give us a profile. So this nice study from New York is comparing a microwave radiometer profile with some of those AMDAR profiles I was talking about. So temperature and humidity, they're difficult to measure, but really important, especially for these coastal cities where there can be very complex structures. Again, Raman LiDAR are also available. They use the UV range, and for that reason, there can be eye safety issues and issues about where you sight them. Moving down to the internal boundary layer kind of scale, what can we do there? So it's clearly still really important to measure surface fluxes, but on this larger scale. And scintillometry comes into its own there. So this is a laser transmitter and receiver with a horizontal path. It's a path average measurement of the flux. Now you have to assume Monod-Nabokov similarity holds along the path in order to invert that and get a flux. But the scale of this is quite impressive. So here's a study from London, from Ben Crawford, showing several kilometre long scintillometer beams and how during a daily cycle we can see the heat flux rising and falling over a wider area. So that is the advantage that we spatially average. Now, it can be used further down, right down into the roughness sublayer, but one has to be careful about the similarity functions that you apply in order to get a heat flux, but there's been some good advances in using that as well. Also at the internal boundary layer scale, this is a new emerging area of unmanned aerial vehicles. So the sort of fixed-wing aircraft you can see in the top right, or the kind of quadcopter, hexacopter version down below. So these are proving very, very useful devices. So this one has had a camera mounted on it. You can take a horizontal path and get very, very high resolution pictures of vegetation, for example. Whereas the quadcopter is better at doing vertical profiles, and here has been used to measure temperature profiles in the atmosphere at a very tricky range, which might be a better resolution than the other remote sensing devices. So they can be tricky to deploy in urban areas, and we look to whether there might be future easing of permissions as to where we can fly them. So this is a very interesting technology. Now, coming down to the ground, where we're a bit more familiar with these flux towers, the famous bubble experiment that Andreas and others conducted. where we have fast response sensors mounted on a tower. It needs to get high enough into the inertial sublayer, at least two times the mean building height, in order to relate the fluxes in the complex roughness sublayer to the inertial sublayer above. So this has been a real stalwart in giving us profiles of fluxes from different areas that we can then, because we get into the inertial sublayer and get the scaling velocities, we can then collapse different results together and learn more generally about urban canopies. So this still remains a very important measurement to be made alongside the deeper measurements. What do we do if we have a really deep urban canopy like New York or Hong Kong or Beijing? Deploying flux towers can be really difficult. And there's another point that if we have a really deep and heterogeneous deep canopy, then we might squeeze out the inertial sublayer. So there's some deeper conceptual issues there. But we have facilities like this fantastic 325-meter high tower in the middle of Beijing, where such flux measurements can be made. But there remains a question mark of, well, what can we do in other cities where we don't have this facility? And one point I want to make is that these tall buildings can just be in clusters, which are not very large compared to their depth, where we may not have a well-developed inertial sublayer at all. So what can we do then in trying to assess the impact of clusters on the boundary there? Well, this is something we've been experimenting in London using Doppler LiDARs to measure building wakes. So what happens here is that the same building Doppler LiDAR, the laser is instead scanning horizontally and intersecting the buildings and their wakes and measuring components of velocity. So here's just one example as this piece of work that Natalie's about to submit. For a southwesterly wind, we can see these two buildings, B and A. They are shedding wakes downstream. And this kind of technique, we can start to look at the length of these wakes and get a sense of how they vary with things like stability. But I think this should open up some questions about what measurements do we need to take where cities are highly heterogeneous. And this might be the dominant paradigm rather than the sort of equilibrium picture we've had before. And how do we do it? So that was a whistle-stop tour of some observation techniques. With these new emerging, particularly remote sensing techniques, we now have data to compare with models that we've never had before. So observations can definitely be used to evaluate models, which are trying ever more daring things. So this is an example from Weather Forecast Model, the UK Met Office Unified Model, a study from Humphrey Lean, where using a nested domain, he's got the grid resolution down to 50 meters. And this is the kind of urban heat island over London that can be resolved at that scale using an LES mode, right? So the turbulent mixing is allowed to evolve. Is it any good? So we have here a height and time plot of the model giving us individual updrafts and in red and downdrafts in blue. So we're starting to resolve the turbulence in these kind of models. And this can be directly compared with turbulence measurements from the Doppler LiDAR. And in a quantitative way. This is just a qualitative comparison. So we have measurements we've never had before that are able to evaluate models. I suggest that we could have models starting to evaluate observations, and this would be really helpful in deciding where and what to measure. And I'm going to borrow a story from the wind energy community in that turbine wakes, similar to building wakes, these are quite pesky because they extend downstream and they can decrease the power output of other wind turbines. So people really want to know how big they are. And there's been a lot of work using Doppler LiDARs to measure the wind speed. So for example, there is something called the Doppler beam swinging scan, DBS, where you point the laser up to the north and to the east, and then you combine all these measurements of wind vector components to give you a single wind vector. Now, if it's a homogeneous flow field, that's all very well and good because the flow is the same here as it is here. Now, if it's not homogeneous, so similar to being in a wake, then the wind vector is changing, and we introduce large errors into the wind profile measurements. Now, what has been done, or has been done in this study by Julie Lindquist et al., is to use an LES simulation to help interpret the observational errors. So we have a wind turbine and its wake being simulated. We have virtual lidars being sampled from within this turbulent flow field. So we have, for instance, profiles from the LES is determined in the black, so that's with all the information possible. And the red is the sampled as if it were a lidar. So we're starting to have these tools, the modeling tools are getting good enough to help support our understanding of the errors inherent in the measurements. Now, can we start using LES more to look at inhomogeneous urban flows, to simulate the observation errors, particularly in these new observations by UAVs, or even if it aids the network design? We can't measure everywhere in an urban area, so maybe we can optimize where we place those measurements. A final point from the workshops was that bring measurements and modeling together is increasingly important, and bringing together as many measurements as possible. So I just want to highlight a few big projects recently that are doing or have done that. So there's the UC squared project in Germany, where focused around the PALM LES model at smaller scales. The Urbisphere campaign and modeling effort is extending out to climate scales, but there's some upcoming quite exciting urban boundary layer measurements to come out of that. The SURF campaign in Beijing was focusing on rainfall and fog around that 325-meter tower I was telling you about. And here in London, we did the ClearFlow project with atmospheric chemists combining urban boundary layer and chemistry measurements. Now, Olympics can drive a lot of innovation, so the Paris Olympics are coming up, and the WMO is sponsoring this project where different forecasting groups are running their models at very high resolution, and there will be some field work associated with that, coronavirus willing. So these urban laboratories are becoming more extensive, and we can learn a lot from them. So I just want to leave this slide, which we can probably come back to. There are still many known unknowns, things we know we need to measure, but we can't yet. Physical modeling, I just put a bit in for that, is still really important. Opportunistic sensing is coming up. It's mostly at street scale and level at the moment, but perhaps it's going to go upwards as we have more drones. And finally, urban data assimilation. Where are we with respect to this, and what do we need to get there? So as you'll hear today, it's essential that observation. And over to Alberto to talk to us about modeling. Let me stop sharing my screen.
Well, thanks a lot, Janet. Thanks for the really nice overview. We'll take questions after Alberto's talk. Alberto is a scientist at Radiometer in Madrid. And well, you all know him from the building energy model, his multi-layer Canopy model. And he's the most recent winner of the Luca Art Award for this year. So the floor is yours.
Okay. Can you hear me and see my screen? Hello?
Yes.
Hello? Can you hear me?
Yes, we can hear you and see your screen.
Yes, and now, oops. Okay. First of all, I'd like to thank you for the organizers for this great idea. And let's start my talk. So I will start with a very stupid question. Why is the urban boundary layer important? And the answer is pretty obvious, because there are people inside. So the fact that there are people in the urban boundary layer is what makes the urban boundary layer unique and what shapes the way we model it. What does it mean? What I mean is that every time you want to simulate a natural system, you have to make a choice, because a model is always a simplification of nature. So you have to choose which part of nature you want to represent better than other parts. And this is determined basically by the reason why you run the model. So why do we run the model usually in urban boundary layer? I can find at least 5 reasons, 5 applications. The first one is certainly air quality. Historically, I think it's been the first reason why people start to study the atmosphere in cities. They want to know the quality of the air we breathe. The second is thermal comfort. So we want to know why and how do we feel. It's directly linked to the thermal comfort is the building energy consumption. So the energy that we use to keep the internal, the indoor space of the buildings to be in a comfort range. Pedestrian wind comfort. So the wind speed in the streets. And the last is weather forecast. So we want to know the weather that will be in the city. If you look at these 5 applications, 4 of them are strongly dependent on the structure of the urban canopy layer. So if we think we want to know the best way to model urban boundary layer, you have to think at these applications. So it's important to keep in mind that in the urban areas, we have a bunch of heterogeneity at different scales, as Janet just said before. So in particular, I want to focus on 2. We have microscale heterogeneity, so the heterogeneity at the scale of the buildings, I would say, so 1 to 10 meters. And this generates structures, wakes behind the buildings or eddies in the canyons that are important, I would say, at least up to the blending height. And then you have another type of heterogeneities, with heterogeneities at a scale 100 to 1000 meters. So this is, for example, the heterogeneity due to different structure between urban neighborhoods, between downtown and other residential areas, or the presence of a big park. And these heterogeneities can generate secondary circulations that can fill up the whole urban boundary layer. So, and together with a circulation at a larger scale, for example, induced by the geography where the city is situated, like sea breeze or slope winds or urban induced breezes. So they are very important to characterize the whole PBL. So if we want to model, usually, historically, people choose 2 types of models. So you have microscale models that run a very high resolution, let's say 1 meter, so they're able to explicitly resolve the buildings. In this way, they can reproduce quite well the macroscale circulation, but for computational reasons today, they cannot be run over very big domains. So the advantages are indeed that we can resolve the macroscale features in the urban canopy layer, but the disadvantage or limitation is that we cannot account for the full urban boundary layer. So as you certainly know, there are different types of CFD models from DNS, so where you solve the full Navier-Stokes equations without any approximation. These models are very accurate, but they are also very computational demanding. So they are mostly used for theoretical studies. Then you have LES, where you parameterize the subgrid motions, but they still need to be run at very high resolution. You have RANS models, where you parameterize the turbulence effect. And then you have another type of models. Here I indicated as highly parameterized fast wind dispersion models like QuickEarth, but there are many others, for example, that became very popular in particular for emergency response after September 11. And now they're becoming more and more popular also for air quality studies. So these type of models, they don't solve the full, they don't solve the Navier-Stokes equations, but they try to parameterize just the main effects like wake behind the buildings or eddies in the streets. And the advantage is that they can run very fast and over big domain. So I would say that this type of models, they are mostly run in neutral conditions. So you cannot really take account of heat fluxes. In this way, For this reason, they are mainly used for air quality and pedestrian wind comfort. Some models like LES and some RANs start to be used in non-neutral conditions, but certainly I think one of the challenges for this type of models is to be able to represent realistic surface heating in realistic urban configurations and be able to validate them. The other type of models is mesoscale models, as you certainly know. So these type of models have the resolution of, let's say, 1 kilometer or several hundred of meters. So they can be run over the whole city, and they can represent the full urban boundary layer. The problems with type of models are two mainly. One is how to represent the impact of the macroscale features, so how to represent the impact of the urban canopy in a certain sense. And the other problem that we are facing with this type of models is that how to represent the secondary circulation that form in the urban boundary layer due to the spatial heterogeneity at the scale of, let's say, 100, 1000 meters. So for the first limitation, as you certainly know, in the last couple of decades, we developed several approaches, several urban canopy parameterizations. Here I just put as an example 4 of them. What is common to all these approaches is that they start by simplify strongly the urban areas. So the city is represented by a very idealized surfaces with, for example, regular canyons, same distance between the buildings and just variable building height. But this is important because thanks to this we can account for 3 different types of active surfaces: the walls, the roof, and the road. In this way, we can also try to account the shadowing and radiation trapping in the canopy. So as I said before, the application of the model is what determines the type of approach. So of these 4 schemes, 3 of them try at least to resolve the feature in the canopy. So they have some estimation, more or less precise, of the characteristics of the urban canopy layer. So they can be used, for example, for applications where it's important to know what's happening in the urban canopy layer. There is another type of parameterization, for example, like the one used by UK Met Office, where the objective is mainly to reproduce the fluxes that are coming out from the urban canopy layer. So they don't care what's happening inside in details. So this type of models are, this type of parameterizations are very good, for example, for weather forecasts, where you don't need to know the details of what's happening in urban canopy. They can run they are not very computationally expensive, so they are very appropriate for this type of applications. The other problem that we have when you simulate urban areas with mesoscale models, as I said before, is to represent the secondary circulation induced by heterogeneity at the scale of, let's say, several hundreds of meters or a few kilometers. For example, here I put a picture of Madrid. You can clearly see that you have the central region, which is the old core with a very dense buildings. Then you have a park here, which is pretty large, and you have another neighborhoods with very different urban structures, and all this will generate difference in momentum and in the heat fluxes. They may generate these secondary circulations. And so I think now we are reaching a point where we have a resolution high enough to resolve these features. But the point is that the turbulence closure that we use are not adapted to this type of work, mainly because they are built on the approximation that the horizontal derivative of mean and turbulent fluxes are 0, which is certainly not the case in this situation. So I think there is a room for improvement here, and I think a lot of work is is doing and will be needed to do in the future to improve these PBL schemes at these resolutions. Okay, this is more or less a snapshot of what we are doing and what we have been done in the last few decades. What are the future directions? So how the urban boundary layer models will develop in the future. I think you have to keep in mind that this type of models are shaped in a certain sense by three forces. One is indeed the scientific knowledge that the understanding we have of how the urban boundary layer works. The other important factor is the computational power, which is a key, and the continuous increase of computational power in the last decades is what was a very important element that allowed the development of all these models. And then you have the type of application, as I said at the beginning. So in the future, I think the 5 application I mentioned before will continue to be important, but we will add another dimension, which is climate change. So for the first time in history now, the structure of the climate is changing at the same pace as the structure of the city can change. So if we think how to modify the structure of the city or how to build a new one or a new urban development, you have to think not only at the present climate, but also at the future climate. And this is strongly linked with urban planning. So I believe that the future developments will take into account these dimensions. And for example, this is a tendency we are already seeing now. I think we'll put more and more attention to understand not only the difference between the urban area and the rural countryside, but also, more importantly, the difference that you have in the urban areas. No? So the intra-urban, the difference in the microclimate, for example, between different urban structures. Here I put a picture of the Buddha project because I think is a very good representation of this growing interest in understanding how different urban structures affect the local climate. Indeed, since we want to modify in a certain sense the urban structure to adapt it to the new climate and the new conditions, we will need models that has the ability to represent this new urban modification. For example, we will need models that are able to represent the green buildings, so green roofs and also green facades, street trees, or rooftop solar panels, for example. The impact of high-performance materials, so that are becoming to use more and more in buildings, for example. We know quite well how these materials behave in the lab, but we still have to work to understand how these materials will impact the urban boundary layer at a bigger scale, for example. And also new modification, like, for example, the impact of electric cars that will modify the air quality, but also the heat emitted by the cars. So we need models that are able to implement this. And we will need models able to assess also the impact, in a better way, the impact of the urban boundary layer structures on people. For example, for thermal comfort, I think we will need to develop more and more models that are able to estimate mean radiant temperature, which is a key variables to assess the thermal comfort. And so far, I think very few atmospheric models are able to do this. We'll need models that are able to estimate better the exchanges between indoor and outdoor, or both heat and pollutants, for example, because people spend a big part of the time inside. And I believe that we have the opportunity to take advantage of, in the modeling, of a range of new, I will say, no conventional information that are coming from a wide range of devices, like cell phones, watches, new cars, and laptops. All these new devices are sensing, in a certain sense, the environment. So if you are able to take and assess the accuracy of this information, we will have a huge amount of information that can be used in many ways. We can be used, for example, to test the model and to improve them, but can be used also to understand how the people behave in the city, how the people move, and how the people what the people do. So this is an important information, for example, to estimate the anthropogenic emission of heat and pollutants. So in a certain sense, I think we have a big opportunity here to deep our understanding of the interaction, of the two-way interaction between a human system, which is the city and the citizens, and the natural system, which is the atmosphere. It interacts in two ways. All these new developments will be implemented in atmospheric models. I think in the near future, we'll still keep the difference between the mesoscale and microscale models, but the gap, particularly in resolution between these two models, will progressively shrink thanks to the increasing computational power. And so I think we still need a very substantial increase in computational power before we will be able to run a full city at 1 meter resolution. But I'm pretty sure that in the next decade, we will see more and more models that were we will try to link the two scales, the two types of models, no? And indeed, we will need to interface these new atmospheric models with a city evolution model for what I said before, to choose the best development that we can imagine for our city in the future. So this is more or less what I want to say. So I'm very curious of the feedbacks. Thank you.
Thank you very much.
So now how can I need to
Stop sharing.
Stop sharing. Okay.
So yeah, Andreas, you want to lead the discussion and the questions, right?
Very happy. Yes. Thank you, Natalie, as well for moderating this. My name is Andreas Christen. I'm trying to now moderate this discussion online, which of course will be different than in a lecture hall, but I'm very pleased to see so many people. We have 100 colleagues here on board. I propose to organize the discussion. You use the raise hand feature. This is a little bit hidden. We first had to figure out how to do that. But if you see the list of participants, click on your name, or not click, move over your name, and then you will see a hand. So we will use that to allow questions on both of the presenters, Janet and Alberto, or also questions on the general future of the discipline. So to stimulate the discussion, please use the raise hand feature, and we, the moderators, will see who has input. At that point, I don't see anyone. Natalie, do you see that? Yes. So I have Marshall Haflin. Do you want to pose a question?
Yeah. Well, just a small question too. I've read that car traffic may actually have a role in the is it the canopy layer dynamics? And some question if a reduction in car in cities can have an effect of actually heating up the surface in a way. That's I found that puzzling question. I don't know if any of you have some information on this.
Well, I guess there was some early work on trying to parameterize the turbulence produced by traffic. I think it was a Trapos project quite some time ago using wind tunnel studies, did quite a lot of this, Petra Klein and other people. That was thinking about the mixing, the heat transfer processes with vehicles. I'm not aware of that much study of that process. It's just that much harder to do. I don't know if Alberto has a comment with respect to his view of what electric vehicles could do. This is still a process that could be.
Yes, in terms of the turbulence, I know, as Janet said, that there are several studies about the impact of turbulence from both the modeling and the experimental points of view. I think mainly in wind tunnels. So there are some studies. I think they were focused mainly on the dynamical impact. So how the movement of the cars affects the mechanical turbulence, in particular for the dispersion of the pollutants. In terms of the heat emitted by the cars, there are some studies. The first one that comes to my mind, I think, is one from Francisco Salamanca over Phoenix. I don't remember exactly the year on the paper, but I can search. So they put it's not very difficult to estimate from the traffic the amount of heat emitted by the cars. And for example, with a methodology similar to the methodology used for the emissions. And if I remember correctly, I think it's quite important, the amount of heat emitted by the cars. Indeed, I mean, it's important. In particular, I mean, it can be several tens of watt per meter, I think. But the important thing is that the peak of heat emitted by the cars is when you have the peak in the traffic, so mainly in the early morning and in the afternoon. So which is when we have the lowest boundary layer height, and when the heat fluxes from the surfaces are smaller. So at these times, they may have a relatively good impact, a very important impact, in particular on the height, on development of the boundary layer height. In the central hour of the day, I think it depends which city you are studying, but I believe the heat flux from the surface is much more dominant. I don't know if I answered your question.
Thank you for answering the question. We have another question from Agnese Salvati, please.
Yeah. Here. Hello. Hello. Thank you very much for the very inspiring presentation. I love them. Well, I work at Brunel University. I'm an architectural engineer, so my background is not climatology, but I'm trying to use urban climate knowledge to investigate especially all the aspects that specifically Alberto Martilli has highlighted in the presentation. So the impact of the three-dimensional urban morphology on thermal comfort and building energy efficiency. So sometimes I've done a PhD on this, and I've worked mainly with the urban weather generator, which is based on the urban canopy parameterization, like the TAB scheme. And I found that model useful for architects or building energy modelers, because it's like kind of targeted to that aim. While on the other hand, sometimes due to my different background, I find difficult to apply other kind of models. So my question was, on the other hand, for instance, to analyze the microclimate at the microscale, I use MVMAT for similar reasons, because it's kind of, easy to use. So my question was to both speakers, do you have some kind of models that you would suggest because of accuracy, or I don't know, that you believe are good or the best we have now to be applied for the specific aim of improving, analyzing thermal comfort and building energy use in urban areas? So considering that architects and designers will use them. Would you have some suggestion? No.
Yes, I understand. I think your point is very important. So we need models that are relatively simple enough that can be used even by people that are not expert in the field. So indeed, I can recommend WRF with my boundary layers, with my parameterizations. But I don't know if other schemes, microscale models, there is MBMet, as you said, but I think MBMet doesn't have a component with building energy models.
No.
There is tough IAUC, I think Negin knows more about this, and which has a building energy model embedded in. I think there is the new Palm 4U that I just read about it. I don't have any experience about using the model, so I don't know how easy it is to use it. But as a general comment, I think one important thing that we have to keep in mind also is that all the modifications. I understand you focus on thermal comfort and building energy consumptions, which are indeed very important. But that you cannot isolate these two effects from the rest. So if you imagine that if you want to modify your buildings to improve the thermal comfort at micro scale and also reduce the energy consumption of the buildings, if you want to apply this strategy at the city scale, this will affect also the behavior of the boundary layer. So I think it's important that you always test the efficiency, the impact of these strategies, not only on what you are interested, so not only on thermal comfort and building energy consumptions, but also on other aspects, for example, air quality. The first thing that comes to my mind is that, for example, if you have a cool roof, you put white roofs, you will certainly reduce the energy consumption of the buildings. But if the strategy is at the city scale, you will reduce the boundary layer height, so you may increase the pollutant concentration. So I think it's important, even if I understand that you focus on one application, to keep in mind that every modification you do to your urban structures will have an impact on the full boundary layer and also on other aspects.
Yeah, thanks. And I just wanted to, repeat the point was that I would like to really have this kind of integrated approach and be able to assess the impact of design decision, like use of cool materials on roofs, facade, roads, not only on street level microclimate, but also at the scale level. I find it difficult because of probably my limitation in the knowledge and in the models that I could use. So that was like kind of trying to have this higher point of view. So I know that, this is in development probably. So,
Yes.
Yeah. So thank you very much. And we note that point that the community needs to work on models that are interactive, scale, overarching, but also applicable not only to the few scientists that work in the field, but to practitioners and to other fields as well that need to link this. Very nice. Thank you. So the next question comes from Megan Nazarian. Please, Megan, can you...
Thanks, Janet. Well, first of all, thank you and congratulations to Janet and Alberto for both the amazing presentation, but also the contribution to the field. I have a question that I'm very curious to hear their thoughts about. Alberto mentioned the interaction with a lot of processes that we look at in our urban climate community and climate change, and also the application that it has. But so far, what we're seeing in the global climate change analysis or even regional analysis, the cities are either ignored or there are some simplistic consideration that are given to that. First of all, I want to know, in your opinion, what are the limitations that leads to this, and also perhaps coming from our outcome of our urban climate field, and what kind of application does it have on the range of applications that, for instance, Alberto mentioned that is relevant for us in the urban climate community?
Maybe I can. Thanks, Megan, for your question. I mean, this is the big questions, right, that we've got to answer. Just to say that, I mean, I think traditionally, climate change projections, they've been constrained to be very coarse, and they've not included urban areas. I think with increased computing power and model complexity, or the greater use of machine learning in these massive models, the resolution of these climate change projections is coming down to capture urban areas. And just a report from the UK, the Met Office released in UK CP18 is the latest climate projections, but there is. Alongside that, a year later, they released a 2.2 kilometer resolution model, which was obviously starting to resolve urban areas and provide data. For example, Bristol City Council, the GLA. So some of the big city councils that are aware of, are aware that these processes are important, are starting to embrace the use of that data. It's going to take time because it's a lot more than they've been used to using, but with the computing power is going to go one way, things are going to be more resolved, and I think maybe one of the jobs is getting these more models that are responsive to different human scenarios and anthropogenic impacts, and the coupling. That's going to become more important. The resolution is going to come, but I think the complexity of the model is the next thing. As Alberto was mentioning, you need to start including people in those kind of scenarios in the model to be useful to the kind of practitioners who need the answers.
Thank you, Janet, for the answer. I'd like to ask Anna Maria Sempreviva to ask a question. Thank you.
Hello, my name is Anna Maria Sempreviva. I'm senior scientist at the Danish Technical University, DTU. I work in wind energy. And my question is about the parameterization of the surface. There is this roughness length, and I would like to ask you, is it still used? What are the frontiers of the roughness length for a town, for the description in the models?
No. So in the reference length it depends on the resolution of vertical resolution, in particular of the model you are using. For example, if you have a multi-layer scheme, if you have a very high resolution in the vertical, what we do in urban areas now is to add a drag force. So we have a drag coefficient instead of the reference length. Probably something that could be applied also for wind turbines. I think instead of, if you have a very high vertical resolution, you can probably add also a drag force with a drag coefficient if you know it. And in general, reference length is the problem of reference length is linked to the use also of the monomorphic similarity theory, and that we know in urban areas very often it doesn't work. So we need to find new ways.
Thank you, Alberta. We have a question from Karam Git.
Yes, hello. So thank you for taking my question. My name is Rit Karam and I am currently a PhD student in Paris. I actually work on the Oasis project, which is co-financed by the European Union, and we are aiming to transforming some schoolyards in Paris into urban green spaces in order to mitigate the urban heating island. I would like to ask you a question about how do we articulate the presence of parks into the cities, regarding, for example, the LCZ, and how do we construct the neighborhoods? Do we take into account, for example, these schoolyards that might become parks, or do these become an LCZ in itself? And how, if there was any research or new models that were emerging from these regarding these specifications. Thank you.
What's the scale of these?
Yeah, so the schoolyards are about, they are not really big, so they are inside the actual schools that are under the responsibilities of the House of the City Council. Sometimes we can go up to 20 square meters, for example, for the biggest.
20 square meter.
Yeah.
Okay, so it's really micro scale.
Yeah, we are really at a very micro scale.
So as I said before, I think in microscale models are so for your purpose, I think you need clearly microscale models. The problem with the microscale models is that often they are not very well, I would say.
I'm sorry. Yes, there's
evaluate. Huh?
200. I think there's a 200. I'm sorry, I just missed the number.
200 square meter is still microscale because it's
yes.
Yeah. So as I said before, clearly you need a microscale model. The point is that there are not many microscale models with that are able to resolve well the heat fluxes, and in particular such this type of modifications. So the presence of the green areas, I think, is still an area that needs to be developed.
Yeah, thank you, Alberto. I'd just like to inform everyone, we try to close in 10 minutes at quarter past, sorry. And we would like to close now with a couple of more general discussion topics. I have one prepared for Janet. The fact that most urban residents, of course, spend most of the time indoors. In most of the more developed countries, it's over 90% of the time we spend indoors, as most of us right now spend time indoors. Is that an area that urban climatologists should intrude and do more measurements, more observations? What could be the limitations, or is that something we should leave for building engineering?
I mean, possibly, if I could add to that, I mean, clearly we can make a contribution. I mean, we understand the external conditions around the houses and the buildings. We understand the flows around the buildings that might determine the exchange and ventilation. Natural ventilation of buildings is. Building engineers themselves say it's really, really difficult for them to simulate, to predict what the natural ventilation of a building is going to be, especially if it's surrounded by other buildings. And I think the heating response of a building surrounded by other densely packed buildings equally, that's a domain that even building engineers need to know about their local neighborhood in a simple way. So I think this community could do a lot at the integration between the outdoor and the indoor realms, and providing simple rules or simple models that could be used by designers and engineers. Definitely.
Thank you. Are there any other comments on that topic from the community? Just before we then close, I would also have a more general question to Alberto that comes from the community as well. The modeling approaches you showed are all physical models. Now, if you follow the developments in computational science, there is a lot of efforts to look into artificial intelligence. And for example, Google has just demonstrated that the short-term forecasting of thunderstorms using artificial intelligence approaches to track radar images of thunderstorms and so on is superior to a physical forecasting in the short term, which is of course clear what we also do when we track thunderstorms and so on. But my question is artificial intelligence modeling something that you consider valuable for urban climatology? And if so, what could be potential applications of artificial intelligence?
As always, it depends on the purpose. So if you want to, probably for a weather forecast or for to forecast something, artificial intelligence could be a fast, a good approach. But the point is that when you want to use the model, for example, to evaluate a strategy, to evaluate a change in some physical parameters, you cannot rely on artificial intelligence, because the artificial intelligence just tell you what happened in the past. So they cannot tell you how the physical system will behave if you change some part of it. So, for example, if you want to know, even for air quality, if you want to evaluate, for example, battery strategies, you need to, you cannot use artificial intelligence. Same if you want to evaluate, for example, a strategy to mitigate the overheating in the urban area. So you need a physical model if you want to evaluate a strategy. And from my point of view, the most valuable use of models is to evaluate strategies, to understand better the physical system, and so understand how the physical system will respond to a change in a part of it.
Yeah, thank you for this closing question. I think we come to the end. We have, of course, upcoming webinars, and Natalie will just in a minute say something in this direction. I also would like to take the opportunity to thank again the two speakers, Janet and Alberto, for their stimulating talks, for the discussion, and it was very nice to also see the engagement despite that we are all here online in times of COVID. And that brings me to the last topic. Essentially, we all have also to ask what are our roles, and what's the role of urban climate in times of COVID? Is there anything we can contribute to essentially look at processes that could mitigate some of the challenges of this disease? Are there also some opportunities, given that, of course, cities behave quite differently now if they are under lockdowns compared to other situations? It could be also an opportunity for research. Those topics will be picked up in the next webinar, I understand, and I'd like to thank the new established committee, which is Natalie, of course, but also Megan, Melissa, and Dev, who has put that up to keep us engaged, the community together, despite of the inability to travel. So thank you, all the four of you, for organizing this. And Natalie, you will say something about the upcoming event.
So the next event will be somewhere in mid-December, and we will celebrate the recent Tim Oak Award winners, which are Scott Crainoff and Chao Ren, and they will be talking about urban heat island mitigation. So the date is still to be planned. It will be in a time zone that is comfortable for Canada and Hong Kong. So will be a bit different than today. Yeah, and in the new year we're going to organize more topic-driven seminars. So starting with urban climate and COVID-19. And I think so. I would like to keep the WebEx open. So if there are more discussion, I will close the recording. But if there are more discussions or people want to catch up, and so I will leave it open for you to talk amongst yourself. So yeah, thank you everyone for attending. It was really nice.
Thanks very much, the organising committee.
Thank you very much. Bye.
Thank you for the great presentations. Bye-bye.